Good morning, Zoom land as well. So let's see, any business we should chat about before we get started with today's material? I'm not seeing any business on Zoom land. Okay. Not hearing anything, so we are going to continue our discussion of the thylakoid reactions. Last time we stopped was just kind of talking about where it happens on the thylakoid membrane. We watched a short video of the overall process, and so today we're going to get into the nitty-gritty details. And as I already mentioned, I like to draw usually on the board these processes, but in order for all of us in class and virtually to be able to see that, I've gone ahead and drawn those and uploaded those videos into our presentation today. So we'll be seeing those as we work through this. I'm not sure that we'll get to the stromal reactions today. If we do not, that homework will be postponed. So I'll probably send around an announcement as well about that and try to change it on the calendar too. Okay. Yeah, so talked about all this. I think we kind of left off right there actually with the Kahoot last week. So let me share my screen with you all. Video, share screen. Okay. So last time we left off with the Kahoot, and we're gonna pick up right now with the first part of the thylakoid reaction. So this is something that I have drawn for you all, and so it's available. All right, so we are drawing the thylakoid reaction, and what we're going to do is orient ourselves. So we're in a chloroplast, and that chloroplast has an outer membrane, and it has an inner membrane, which is actually highly folded into these pancake-like structures. So one pancake would be a grana for plural, and an individual pancake within that is a thylakoid. And so what I have below is the thylakoid itself, which has a double membrane. We have blown up one of those thylakoids, and we're going to look at the membrane. So I've already drawn that double membrane here, so you can see it. We don't waste time with me drawing it. And what we're going to do is look first at the different photosystems. And so inside my thylakoid, that space is referred to as the lumen. So this is that thylakoid membrane. And then outside my lumen, down here, we're looking at the other thylakoid right abutted along with this one. But bathing the thylakoids is the aqueous stroma. And be careful here, stroma has an R. It's not stoma like the opening in a leaf without the R. All right, so there are two photosystems in the thylakoid membrane, photosystem 1 and photosystem 2. And we're actually going to start first with photosystem 2, which starts our process, while photosystem 1 is the one that was discovered first. So we've just oriented ourselves so far. Actually, let me turn that light on for you. So lights on. Okay. So we're in that thylakoid membrane. We're starting to think about those two photosystems. I always forget how to get back to my presentation. There we go. Okay. Is this what I want now? Let's just try this again. Okay, so those two photosystems that I was referring to are drawn here for you. Photosystem 2 and photosystem 1. As I mentioned in the video, photosystem 1 is the one that was discovered first, so that's why it has the number 1. But when we talk about the process, we're actually always going to start with photosystem 2. That'll become more clear why we start there in a moment. A photosystem contains the special reaction center that we've already talked about, those two chlorophyll A molecules. And along with that, we have our chlorophyll A, chlorophyll B's, accessory pigments, all of this being referred to as the antenna complex as part of that photosystem. Each photosystem has a slightly different special chlorophyll A reaction center. And so photosystem 2, its reaction center will often be shown as P680. What that's referring to is the fact that these two chlorophyll A molecules actually absorb better or best at the 680 nanometer. So that's where kind of, yeah, that's how they differ slightly from the other reaction center. For photosystem 1, it actually absorbs a little bit better in the 700 nanometer range. So they're slightly different, and you might see them referred to as P680 or P700, and that's why. In both photosystems, light is going to come in and bounce around that antenna complex until it comes to that special chlorophyll pair in the middle, at which point the electrons will be boosted in orbital, and we're going to talk about that next step where they're grabbed by the electron acceptor. In both photosystem 2 and photosystem 1, that process acts. We'll also talk a little bit about photolysis in a moment, which is particular to photosystem 2. It has a special area that's in charge of that. So let's go ahead and go into a little more depth on those two photosystems. Again, we're going to go through a drawing, and I'll detail those again for you.
All right, so we are going to focus in on that thylakoid membrane and look more closely at photosystem 2. Photosystem 2, the major pigment in that system is chlorophyll A, and we're going to have a lot of those. That is the most numerous pigment in plants. Lots and lots of those embedded in the membrane. Remember, chlorophyll A has that fatty lipid tail, so it can stick right in there. The other molecule or pigment that we'll have a lot of is chlorophyll B, and that's the second most common pigment that we have in our photosystems. Remember, there's just a small difference between the two in the hydroxyl group. And the other pigments that we have are accessory pigments. And those include zeanthan, carotenoids, all kinds of things in there. So we'll have lots of helpers in there. And then I want to go back to our chlorophyll A again and talk about our two really special ones, two chlorophyll A molecules that are known as our reaction centers. And our reaction center for photosystem 2 has its best absorption at 680 nanometers. So often you'll see the reaction center labeled as P680 for photosystem 2. So there's our photosystem 2. And you might see it as PS2 for short. All right, now let's look at our other photosystem. And we'll put that in there. Okay. And our other photosystem will be a little further away there. Yeah, we can blow that up. It's going to have a similar set of pigments, so it's going to have lots of chlorophyll A's again. Again, the most numerous kind of pigment embedded in that membrane. And we're going to have some chlorophyll B's, the second most common pigment. And we'll have some accessory pigments. So those are the ones that you get to see in the fall. The oranges and the yellows and the reds, the carotenoid xanthans, and things like that. And then this one also has two special chlorophyll A molecules as its reaction center. But this time, these pigments absorb best at 700 nanometers. So sometimes you'll see it indicated like that. All right, so we have our two photosystems embedded in our membrane with our reaction centers. So now we're going to talk about the transfer of electrons.
Light on. All right, so those are our two photosystems. I really should figure out how to like escape. I don't know. Do you guys know? Okay, so here's the full model of the thylakoid membrane with the two photosystems embedded. Here's our photosystem 2. Here's our photosystem 1. There's our reaction center with those two special chlorophyll A molecules for photosystem 2 and for photosystem 1. Now what we're going to do is we're going to excite the electrons from the reaction center. We're going to grab it by an electron acceptor, pass it down an electron transport chain until it reaches photosystem 1. We're going to give that electron to photosystem 1 where it is re-energized by light. It boosts that electron back up in orbital again, and then it will undergo a much shorter electron transport chain until we reach our final electron acceptor, NADPH. Don't confuse this with cellular respiration, which is NADH for that final electron acceptor. Here we have a P, and how I recall that it has a P is that it's photosynthesis, okay? So our final electron acceptor during the thylakoid reactions is NADPH. And electron acceptors, basically what we're gonna do is we're gonna take this to our next set of reactions, the stromal reactions, and we're gonna use the energy. So we're gonna temporarily store the energy in the electron acceptor, and then we're gonna use it later on. What I like to think about, or how I like to think about electron acceptors is that they're kind of like checks. Like you write a check and then you take it to the bank and then you can cash it. That's basically what's happening here. You're writing out a check for energy, and then later on you're gonna take it to the bank and cash it out and get that money or that energy back out, okay? All right, so we're using photons or light to energize an electron. That's going to boost its energy way up. Then we're going to pass it along an electron transport chain. While we're doing that, we're going to use a little bit of its energy to do some work, and I'll explain what that is in a moment. So that's why you kind of see this as going down in energy a little bit, because we're going to kind of siphon a little bit off during that process. That means that we have to reboost it. We have to re-energize it by adding light back into the system during photosystem 1. We'll reboost it, and then we'll pass it again to our final electron acceptor, NADPH. Okay. All right, so.
All right, so we're picking up where we left off. We have our two photosystems. So photosystem 2 over here, and then photosystem 1 that we just finished up with P700 as its reaction center. So let's go back to photosystem 2, and what's going to happen is we're going to get light coming in, hitting the leaf, passing through, and eventually those photons are going to be absorbed by the pigments. Once that happens, the energy that's transferred will go from pigment to pigment to pigment until that energy is absorbed by the reaction center. Okay? So that energy boosts an electron from the reaction center. It actually boosts 2 at once, but let's just concentrate on electrons. And once that electron is boosted, what we're going to do is there's going to be another molecule, Johnny on the spot, and that molecule is another protein called plastoquinone. All right, so we're going to put kind of just a circle in here to denote plastoquinone, and it is an electron acceptor. So we'll write that out for us. So it grabs the electron from that outer orbital where it was boosted by all of that resonance energy being focused into that reaction center. So that electron gets boosted, it gets grabbed by plastoquinone. Plastoquinone is then going to transfer that electron to a very special protein. And that next protein is actually a complex of different proteins called cytochrome B6F. Okay. I'll draw that spanning the membrane here. And I'll shorten it here. But I'll spell it out. So cytochrome B6F. All right, so that's a complex of proteins. Plastoquinone and cytochrome B6F are going to work together. So that electron from plastoquinone gets shuffled to cytochrome B6F, and then we have another protein enzyme down here inside that membrane called plastocyanin. That's basically going to be a shuttle from our cytochrome B6F to our photosystem 1. Okay. Now, during all that shuffling, a lot of the energy has been lost from those electrons, so they're not quite as energetic as it was. So we're actually going to re-energize the electrons inside photosystem 1 so that the electron, I'm going to erase that so it's not in our way. so that that electron is boosted once more in orbital, and this time it's going to be picked up by a very short electron transport
chain. Light on?
We got the one part of that right, except the second part. Didn't get changed ever.
No, but we'll pick that up, I promise. Okay, so we have that second, and at the end of the second electron transport chain, we're gonna pick up and see NADPH there. All right, so during the electron transport chain, we're gonna even put another level of complexity here, okay? What I just described to you is the non-cyclic photophosphorylation. Let me explain what that means exactly. So we have our electron that's boosted. It's passed from photosystem 2 to plastoquinone to cytochrome B6F to plastocyanin to photosystem 1 to ferredoxin NADP reductase, and finally to our electron acceptor NADPH. That is a line. It's non-cyclic, it's linear. When it's being passed from plastoquinone to cytochrome B6F, they're going to be slightly negatively charged because of that electron. And during that time, plastoquinone, while it has hold of that electron, is going to grab a proton from the stroma that's bathing it. Remember, that's an aqueous solution, so we have free protons available. So protons are positively charged, which are attracted to the negatively charged electron. So the plastoquinone is going to grab that proton. It's going to pass it to cytochrome B6F together, and then cytochrome B6F is going to pump it across the membrane into the thylakoid lumen. What we are doing is building a battery. Maybe you didn't realize, but all batteries work on a separation of charges, and they give you energy by allowing charges to flow. That's what we're gonna do here. So we're building up a battery right now. Another way to think about it is a lake of protons, and we have a dam with a turbine or a generator, and that dam allows water to flow down. It turns the turbine and produces electricity. We're gonna do something very similar here. So we're gonna build a lake of protons in a lumen by this pumping action. If you recall your information about how diffusion works, diffusion can go down a concentration gradient without any energy input. However, we're going against a concentration gradient here. We're increasing protons in the lumen. It's a higher concentration of protons than outside. So we're actually going to use a little bit of energy from that electron to do that, to force the proton across the membrane against its gradient. So again, we're losing a little bit of energy of that electron there to do this work, to build this lake of protons. This is why we have to re-energize it during photosystem 1 to give it to our final electron acceptor. This lake that we're building of protons, we're gonna let it go through a dam and turn a turbine. It's a molecular dam and a molecular turbine, but still no less awesome. So in this case, ATP synthase is going to be our turbine. We'll let protons flow down their concentration gradient, just like water flowing down a dam, and that will turn this turbine. And we're going to use that to force a phosphate onto ADP, turning it into ATP. You might recall that that is the energy molecule during cellular respiration. That's how your body does everything, is from ATP. Well, plants have mitochondria to do everything too for them. What we're going to do with this ATP is we're going to use it specifically to run this next set of reactions, the stromal reactions. So we're going to take NADPH, we're going to take ATP, and we're going to use it to run the second set of reactions. All right, so let's go back to this word, non-cyclic. We have a linear passage of electrons from photosystem 2 all the way to, well, really water, which I haven't mentioned yet, all the way to our final electron acceptor, NADPH. So it's non-cyclic. Photo, meaning light. We're using light to run this process, right? It's coming in, hitting photosystem 2, hitting photosystem 1. So there's the photo part. And then the phosphorylation is this part. We are phosphorylating ADP into ATP. So that's this whole process that we're seeing, non-cyclic photophosphorylation. There's a little bit more to the story, of course, and that is the lake that we're building is not big enough unless we also do this. This is called cyclic photophosphorylation. In this case, we are going to pass an electron through plastoquinone, cytochrome B6F, plastocyanin to photosystem 1, but this time we're not passing it to our final electron acceptor. What we're going to do instead is we're going to boost that electron and give it back to plastoquinone. When we do that, what are we going to be able to do more with now? We're going to be able to pump more protons across. So now, with cyclic photophosphorylation and non-cyclic photophosphorylation, our lake of protons is big enough to run our turbine that we need to turn. So both processes work together to form enough ATP. Questions about the distinction between those two? Okay, so I'm going to draw all of that happening for us.
All right, so now we are going to look at the electron that we just boosted, and we're going to, it's going to have one of two fates. It could either be picked up by ferredoxin and passed to ferredoxin, flavoprotein ferredoxin NADP plus reductase, to be picked up by our final electron acceptor, NADP plus. As it picks up that electron, it also picks up a couple of protons and becomes NADPH. So in the thylakoid reactions, this is our final electron acceptor, and we'll see this NADPH play a role later in the stromal reactions of photosynthesis. And you don't really need to memorize FD and FDNR, but I will write those out here. So ferredoxin, and then FDNR, or FNR, there, ferredoxin, NAPP plus reductase. I don't know why I always forget the flavoprotein for that. Okay. So that's that other electron carrier there. The other potential fate of that electron, so in this case, it got passed to FD, FNR, and then to our final electron acceptor there. That whole series of events, the electron going from photosystem to plastoquinone, Thylakoid B6F, plastocyanin, photosystem 1, and being picked up by our final electron acceptor, that is known as the non-cyclic portion of photophosphorylation. I don't think that's going to fit. Sorry about that. The other potential fate for that electron is actually to get picked up by plastoquinone and go back through that process of plastoquinone, cytochrome B6F, plastocyanin, photosystem 1 to get reboosted, and it can either go again into that portion or it can get picked up by that final electron acceptor. So each time it's boosted from photosystem 1, it'll go into one of those two possibilities. When it is instead thrown back over to plastoquinone, this is known as the cyclic part of photophosphorylation. All right. So next what we're going to talk about is this electron that basically we just took away and how we get that back.
Light on. All right, so we went through cyclic and non-cyclic photophosphorylation, and hopefully you realize that we took electrons from our reaction center. We have to replace them in order to keep this going. Right? We can't keep taking electrons from nothing. So in order to keep this whole process going, we have to replace those electrons. And the process that replaces those is photolysis. Photo for light, lysis for split. So we're going to use light to split water. Water is great for this, again, because water is non-toxic usually, okay? We're going to have light coming into our photosystems, remember, and part of that energy is going to be used to split water, We're going to strip it of 2 electrons to give to our reaction center. Let's see, H2O, okay? So we took out electrons. It's going to leave us 2 protons, H plus and H plus, which is great because we're trying to build a battery inside here anyways. So more protons, the better. And then we also have some oxygen. So oxygen is not going to stick around. It's going to diffuse out of the leaf. And in fact, we used this process of photolysis to measure photosynthesis in lab this week. Remember, we sucked out all the air from the leaves and in that spongy mesophyll layer, we sucked out all the gas. And then we measured photosynthetic rates by those leaves refilling with gas and floating to the top. That gas was most likely oxygen. Some of it could have been carbon dioxide from respiration, but most of that was oxygen. And you can see this process directly through aquatic plants. This was Aqualesia. You might have this in your aquarium with little gas bubbles. Those are little oxygen gas bubbles coming off there because of this process, because of photolysis. Okay, so we're going to take water, we're going to add light to give us 2 electrons, 2 protons, and a half of an oxygen gas molecule. So let's watch that part in the drawing.
All right, so now, you know, we've had this electron moving along the electron transport chain and being picked up by NADP plus to become NADPH. Now that electron is going away from this thylakoid membrane. What that means is that somehow we need to replace that electron that's getting boosted from our photosystem 2 so that this whole transport chain can keep going. And we do have something that will do that for us. So there's another piece to photosystem 2, and that is called the oxygen evolving complex. And as the name suggests, during this process, we're going to get oxygen out. So what we have is water, and through a process called photolysis, that water is going to be split into its components. So H2O gets picked up by the oxygen evolving complex. And what we're going to get out of that are some protons, oxygen, and the protons are positive, so what happened to our little negative guys? Well, the electrons are going to be stripped off and given to our reaction center to replace its missing electrons. The oxygen that we just made is going to diffuse out. And it's going to diffuse out of, remember where we're at. I do this earlier, so let's go down there. Remember, we're in the leaf, and we're in one of these chloroplasts. We're in the thylakoid membrane, so we just need some oxygen. Okay, oxygen is a small non-polar gas, so it can diffuse right through that membrane, right through that membrane. And we're here in these chloroplasts, and so now that oxygen is diffused out of the membrane, it will wind up in these air spaces, and at that point it can diffuse right out of the open stoma. And we're going to revisit these little holes in the leaf, the stoma for singular or stomata for plural, that are being opened and closed, those holes, by guard cells. So let's go back up to photolysis there. All right, so we've just split off an electron, and that electron is going to go now through the electron transport chain, and we're actually going to use it now to do a little bit of work.
Turn that light back on for us real quick. So I already mentioned the plastoquinone and cytochrome B6F. This is showing you a model of that process of the proton being pumped across the membrane. So here's our phospholipid heads and tails, that cytochrome B6F going right across that membrane, being embedded in it. And then plastoquinone is part of and is associated with that cytochrome B6F. So we have protons outside in that aqueous solution of the stroma. They're going to be grabbed by plastoquinone while it has access to the electrons, and it's a little negatively charged. It's going to grab that positive charge. It's going to pass both to cytochrome B6F, and cytochrome B6F is then going to move the proton across into the lumen of the thylakoid, and it's going to pass that electron off to plastocyanin.
All right, so we're back up here with our oxygen evolving complex, where light energy came in and some of it was used to split that water apart during photolysis. And we have these protons right here, and let's talk about what's going to happen with those protons. All right. So we're building up protons from each molecule of water split. We get 2 out, and we're actually getting ready to build a battery. And just as in any battery, it's basically a separation of charges. So you'll see that we have positive protons, and we're just going to keep building that charge. How we're going to do that is during this electron transport chain, we're going to use some of the electron's energy to help build a gradient. All right, so remember the stroma. The stroma is an aqueous solution, which means it has HOH, or water. And water is a fantastic molecule. It does some really crazy stuff. One of the things that it does, because oxygen is so electronegative, is it will temporarily hold on to the hydrogen's electron, and so you'll get the molecule temporarily existing as a proton and a hydroxyl. When that happens, plastoquinone is going to be able to pull that proton down because it's slightly negatively charged when it's holding onto its electron. It is going to pull it down and pass it to the cytochrome B6F, where it gets pumped across that membrane. So it actually requires a little bit of energy, and that energy is coming from that energized electron that's being passed through that electron transport chain. So this is happening during the non-cyclic portion of this process and the cyclic portion of this process. And this is why we think that both cycles exist, both the non-cyclic and the cyclic photophosphorylation exists, is to really get protons pumped across that membrane. All right, so we're building protons in this lumen space so that at some point it becomes relatively acidic compared to the outside area, which becomes relatively basic. Okay. And so we now have a battery, right? We've got a slightly acidic pH here and a slightly basic pH on the outside. And now what we're going to do is use the battery that we just built by pumping protons across the membrane to run photophosphorylation.
Okay, so all we've seen, all of this passing of electrons and picking up electrons, it's really how biological systems do most of their stuff, which is redox reactions. So redox means reduction, oxidation reactions. So they're just paired with one another. And redox for reduced, we have an oxidizing agent, and we're going to pick up 2 electrons and be called reduced. It's going to be paired with a reducing agent with 2 electrons that is then gives them up and is then oxidized. So these work in concert. One way that a student told me that they remember which is this mnemonic oil rig. So oxidized is a loss, reduced is a gain of electrons. So hopefully that will work to help you recall which is which. And we're just, this whole process of photosynthesis is really just pairing redox reactions. So if we look at the overall equation, we haven't talked about the carbon dioxide part yet. We will. It's going to become reduced and water has become oxidized. So even on the grander scale of things, we have a redox reaction happening. The turbine that is going to be able to throw on the phosphate groups is ATP synthase. And we're going to pick up with that turbine and talk a little bit about it next week, next Monday, which means no stromal homework for next Monday. Actually, we're not going to talk about it next Monday. We'll talk about it next Wednesday because Monday's Labor Day. Okay. All right, that's the end of class. Any questions as you guys leave? Okay. All right, I'll see you all on Tuesday, or yeah, Tuesday for lab. Don't forget to print your lab. Have a really good weekend. Hopefully you get to relax a little bit.